We have finished our lectures on all of the engineered materials, ordinary materials, mixtures, metamaterials, and photonic crystals. So it's no coincidence that this lecture follows that. Through all of these lectures, we've talked about these metamaterials, photonic crystals, these engineered materials somehow realizing an overall effective set of electromagnetic properties. So a good question comes up, given a engineered material of some sort, how do we determine what those effective material properties are? What are the issues that we encounter? That's simple in concept, but as you'll see, it's a pretty involved answer, and it's not easy. A lot of lectures we talk about here are short. This one is not short, and it's heavy, and there's a lot of complexities to it. So I'll start at a 60,000 foot level, and then we'll fill in the details. The 60,000 foot level is the introduction, and I'm just going to step you through a bunch of different ways that folks have taken their metamaterials, photonic crystals, whatever they are, and determined the effective properties. And as far as I'm concerned, the jury's still out on what is the best way, and certain ones work better in certain circumstances than others. But the best I can do is just shotgun you with all of the different methods and let you decide and give you a good understanding of what's here. So what is this topic that we're calling parameter retrieval, or also a lot of times called homogenization? So let's look on this slide. We see we have a cartoon of a metamaterial, a photonic crystal, a mixture, whatever it is. That there's some weird material here, and we can model or measure the scattering from that. We hit it with an incident wave from the left, it will reflect or transmit. Likewise, if we hit it from the right, it will transmit or backward reflect. And so we call those the scattering parameters. And we can either simulate those or model them. Now, if we can come up with a second material that is homogeneous, so it's a smooth, continuous material with some set of electromagnetic properties, and if for the same thickness, if we could simulate that and get the same scattering parameters than we did above up here, these would be the effective electromagnetic properties of this metamaterial. So it's a one-for-one replacement of your engineered material with homogeneous properties. We call those the effective properties. Simple in concept. How do we determine those? Here is what I think a good example is of the troubles that we encounter. So bring your eyes to this middle diagram right now. What we have is a finite difference frequency domain simulation of a subwavelength grating. So we're looking at the cross section of the grating. Here's one tooth. It has a dielectric constant of 6, and then it has air gaps between the teeth. And of course there's air on the top and the bottom. So the question is, given this slab of thickness D, what are the effective material properties of that? If we do that correctly, we should be able to replace our grating with a homogeneous slab with this effective dielectric constant, same thickness, and then we would see the same transmission and reflection. Now let me try to explain this set of data. What I do is I simulate this grating one time and I calculate whatever transmission and reflection we get from this. That would be R meta and T meta. So that's the transmission and reflection of this metamaterial. Then I make a whole bunch of guesses as to what the effective dielectric constant would be. Since I'm making this out of something with a dielectric constant of 1 and 6, I know that this has to be equal to or greater than 1 and less than or equal to 6. So what I can do is I can set up a sweep of the effective permittivity from 1 to 6, and I can try each one. And so then I calculate, I pick an effective dielectric constant, calculate the transmission and reflection using a technique like transfer matrix method. And given those, R homogeneous and T homogeneous, I calculate an overall error. And what you're seeing here is the error of doing that. So I'm increasing at the same time both the thickness of the grating and the thickness of the slab so that they're both the same. And for each thickness, the horizontal axis is thickness. For each thickness, I sweep all of the possible effective dielectric constants, and I calculate the error. So for effective dielectric constant and thickness of the slab. In principle, as I change the thickness, if this does really act like an effective material, that should not change its effective properties. We have seen in our subwavelength lecture that for really, really shallow gratings, that's not necessarily the case. But here we have a pretty deep grating, so that's not really the issue. So we plot the error. What do we see? We have this minimum traveling straight through. Well, that is our actual answer. So the actual effective dielectric constant of that grating region is somewhere around 3.2. But notice we have these other minimum regions. And as we go to thicker and thicker gratings, there's more and more of these possible answers. And in fact, if this were fixed to just one slab thickness, in fact, there are multiple correct answers. So how on earth do we determine which of those is the correct answer? And in fact, there is none, because they're all correct answers. This acts like all of these. And so this problem is called branching, when there's multiple correct solutions. And that is why this is so complicated, because we have to sort this out. How do we handle these multiple correct answers? What we've done here is this is a simple case, so it wasn't too bad to calculate all this, but for more complex metamaterials, it's prohibitive to generate a big set of data like this. But if we have it, well, clearly, here's our answer. These other ones are not answers, or they would be traveling straight across this array of data. So that's called branching. That's what complicates things. There actually are multiple correct solutions, and we need more information in order to sort that out. Another thing that comes up is, for lack of a better title, I will call it degrees of freedom. When we measure transmission and reflection through a device, we actually have measured 4 different numbers. We have the real and imaginary part of the reflection and the real and imaginary part of the transmission. That's 4 numbers. So what we have to do is think about how many things we want to determine. So if we want to determine the complex permeability and complex permittivity, we need to remember that's actually 4 numbers, right? Because we have the real and imaginary part of permeability and the real and imaginary part of permittivity. So if we have 4 numbers, that means we need at least 4 measurements to determine those. So we need 1 measurement of the complex transmission and reflection in order to determine the permeability and permittivity. If we only had 1 measurement, maybe we've only measured reflection, it's actually not possible to determine what the complex permeability and permittivity is at the same time. Now, if we know something about the material, maybe we know it has a negligible magnetic response, well, that means the permeability in that case is known, so we only have 2 unknowns, the real and imaginary part of the permittivity. Well, maybe we could extract that from just a reflection, because then we'd have 2 numbers, and we're trying to determine 2 numbers. So keep this in mind. If we're trying to determine 4 different numbers, we need 4 measurements. We can't do that on 2 measurements or 1 measurement. We need at least 4. Our first parameter retrieval technique that we'll discuss is S-parameter retrieval. It is common to see this in the literature, and this is also what would happen in the lab if we measured scattering from a device. How do we take those scattering parameters and figure out what the effective material properties were? To reiterate what we said a few slides ago, essentially, if we have a metamaterial, photonic crystal, mixture, slab, whatever, and we measure the scattering parameters, if somehow we knew the effective properties of that, we could replace that same thickness, but with a homogeneous slab with those effective material properties, and measure the exact same scattering parameters. So for the inhomogeneous case or the metamaterial case, we would get this scattering matrix. Using our effective material properties, we get this second scattering matrix. And so the idea is, if these really are the effective material properties, our 2 scattering matrices are the same. That's the start of this. So here's the process. We start with either a simulation of our engineered material, or maybe we have this in the lab and we measure the scattering parameters. So we come away with our scattering parameters. From this, through a mathematical process, we can extract the effective refractive index and the effective impedance of that material. Given these, we can then extract the permeability and the permittivity terms. So we'll do two things. We'll do what's called a forward analysis. We'll say, okay, given certain material properties of a homogeneous slab, how do we calculate, theoretically, the scattering parameters? And once we have that formulation, we'll have our scattering parameters in terms of the material properties. Then we can mathematically invert that so that if we're starting with the scattering parameters, we can extract the material properties. That seems simple in concept, but let's see what happens. We need two intermediate parameters. First, we have little r. This is the local reflection off one of the interfaces. So for example, we're going from air into this slab with some refractive index and some impedance, or some permeability and permittivity. So we get a little reflection coefficient here. And so that's little r. Second, once we have a wave inside the slab, and it propagates once across the slab, it accumulates a certain amount of phase. We'll call that the single pass phase, and we call that T. So that's e to the j. K0 is the free space wave number, n is the effective refractive index of the slab, and d is its thickness. So this is a single pass transmission coefficient. It does not take into account any kind of scattering at the interfaces. That will come next. We know if we have a slab, we have an incoming wave. Some of it reflects at the first interface. The rest of it transmits. When it hits the second interface, some transmits, some reflects. And this bounces back and forth. We get multiple reflected waves. We get multiple transmitted waves. We add all of these up to get an overall transmitted wave. And we add up all of the reflected ones to get an overall reflected wave. So the overall reflected wave is S11. And the overall transmitted wave is S21. And then due to symmetry of the problem, we can also get S12 and S22. But now we have our scattering parameters in terms of R and T. And on the previous slide, we had R and T in terms of our refractive index and impedance. So really what we have now is our scattering parameters in terms of the material parameters. So here are our four equations. Here's our scattering parameters in terms of R and T, and then we also have R and T in terms of the refractive index and material impedance. So now this is simple. We simply invert that to calculate impedance and refractive index from our two scattering parameters. So how do we do that? Well, after a bunch of algebra, we can arrive at some equations, but we're going to have problems. Looking at the first equation, we have impedance that we can solve, but we have this plus and minus of a square root of a number. We have to resolve that. So in order to resolve many things, we make an assumption now that our engineered material is passive. There's no gain in it. There's only loss. And there's a lot of things that implies that we can use to resolve signs of things. First of all, we look at impedance. Impedance is a resistance plus a reactance. Well, if we have a passive material, the resistance has to be positive. So the real part of impedance has to be greater than or equal to 0. Let's look at refractive index. Refractive index is the ordinary refractive index plus the extinction coefficient. Remember, this is almost the attenuation coefficient. This is responsible for decay. Well, if we have a passive material, that wave has to decay, not grow. So this kappa, the extinction coefficient, has to be a positive term. So the imaginary part of refractive index has to be greater than or equal to 0. We have the same argument here for both the permeability and permittivity. We know from previous discussions in the Lorentz model that if there is an imaginary component, that we will have loss if this is positive. That does not mean these terms are solely responsible for loss. Once this becomes non-zero, the real part also contributes to the loss as we've seen. But this has to be positive for loss. If it were negative, that would imply gain. So the imaginary components of both mu and epsilon also have to be positive quantities. So the imaginary parts, mu and epsilon, greater than or equal to 0. Overall, these four equations summarize the conditions for having a passive material. And you have now some of the details behind that. Let's think about this impedance equation. This just came from a direct inversion of our equations. The only ambiguity here is the sign, this plus and minus. Well, we have this condition. The real part of impedance has to be greater than or equal to 0. Well, if we just look at the square root, just think of this as being a positive number. It will have a real and an imaginary part. We ignore the imaginary component and look at the real component. If that's positive, we're done. If it's negative, then clearly we needed to put a negative out here, and we invert the sign on both the real and imaginary parts. So here's a little MATLAB script of how we can sort all that out. So impedance is a pretty easy one. We can get that straight from the scattering parameters, just one little sign to sort out. Now, if we knew that our material did have gain, then we might say that the real part of impedance we know has to be less than or equal to 0. But most engineered materials are passive materials, and this assumption works very well. The second parameter we want to calculate, and we're not finished this story yet, but we want to calculate the transmission coefficient T. That's the single pass phase, if you will. That's straightforward. There's no ambiguity here. So at this point, we know the impedance, and we know that transmission coefficient T. Remember, T was e to the jk n times d, but that refractive index was a complex number. So rather than write it as ordinary and the extinction coefficient, I'm just putting in n prime for the real part and then double prime for the imaginary part. So if we expand that, we get a complex exponential. That's an oscillation, and we get this, the real part, which comes from the imaginary part of n, but the argument in the exponent is completely real. This is decay, and that's why we said that this imaginary part of refractive index has to be positive. That means we have decay. If the imaginary part were negative, we'd have an overall positive number, and this would grow exponentially. So now we have T in terms of the real and imaginary parts of refractive index. How do we invert this? Well, since we have exponentials, it makes sense that we would take a natural log. So we look at this equation and we take the natural log of both sides. And we use our rules of logarithms, and we end up here. But we have to take the natural log of a complex exponential. It seems as simple as taking this argument and bringing it to the outside and just saying, oh, well, the natural log of this complex exponential is just that. It turns out that is not correct. And if it were, this would be really simple. But unfortunately, that's not correct, and this becomes much more complicated. This is branching. Let's think about a cosine. What is the inverse cosine of 0.5? The quick answer is 60 degrees. Well, I would argue that's not correct. In fact, there's an infinite number of possible answers. It's 60 degrees plus or minus integer combinations of 360 degrees, right? Because if we go around the circle one time, we end up at the same angle again, yet that is another possible answer of what the inverse cosine is of 0.5. So there's an infinite number of answers. And we have a complex exponential, that's a trig function, and we have to do the same thing. So it's not just j times k naught nd, we have to subtract an integer multiple of 2 pi. So m is an integer, and that is what's responsible for all of these different branches. How on earth do we know what m should be, that integer m? So let's do the inversion. This top equation is where we were a couple slides ago, and we realize now when we take the natural log of this complex exponential, it's actually an expansion with an infinite number of terms. We're adding and subtracting an integer multiple of 2 pi. So the natural log of t is actually equal to this. Now we can look at the real and imaginary parts of this natural log of t. The real part of the natural log of t is the real part of the right-hand side of the equation. That's just minus k naught n double prime times d. We can look at the imaginary component of t, which is simply the imaginary component of this expression. That's k naught times n single prime times d minus this integer multiple of 2 pi. This first equation we can use to calculate n double prime. That's the extinction coefficient, or the imaginary part of refractive index. That's down here. So t we know. Remember, we calculated t without ambiguity. We can take its natural log, we can calculate the real part, we can divide by k naught d, and then take a negative sign. So there's no problems finding n double prime. The branching occurs in n prime. That's the real part of refractive index. That's the ordinary refractive index, and that's the 1 over k naught d. We have the imaginary part now of natural log of t, plus this integer multiple of 2 pi. It makes sense it would appear here. Remember, the ordinary refractive index tells us how fast the wave is traveling, or how compressed the wave is. Waves are cosines. They repeat every 2 pi. So since the ordinary refractive index is tied much more intimately to that, it makes sense that's where this branching thing would occur. But we still have yet to sort out the branching. How do we determine what is the correct value of m? And without knowing anything else, all possible combinations of m are correct answers. The only way we can determine anything better is if we somehow know more information. So here is one way to resolve this branching problem. But remember, we are required to know something else. And that something else is knowing the refractive index at a previous frequency point. So we will call the previous frequency point f naught. And we'll say that we somehow have magically determined the refractive index and impedance at f naught. Now we want to do the parameter retrieval at frequency f1. So what can be done now? Let's pretend we know the f1 point as well. We can fit those to some kind of curve. And in this case, we're using a Taylor series. So we can write our new point in terms of the old point expanded into a Taylor series. We're essentially doing a curve fit. Okay. If we look at our expansion and we drop the higher order terms, we have a binomial equation here. We know that the solution to this will have 2 roots. So there are 2 possible refractive indices that will satisfy this equation. So first, we look at the imaginary part. We already know that without ambiguity from what we did on previous slides. So, but this gives us 2 possibilities. We choose our root of the one that gives us the closest imaginary component to the one we calculated on a previous slide. So 2 possible roots. They have a real and imaginary part. Right now we're only looking at the imaginary parts. One of those has to come close to the imaginary component that we already know it should be from a previous slide. The second step now is to choose the branching. What is the integer m? Well, we've already chosen the root. Now we need this integer m. Well, we choose the m that gives us the refractive index closest to what we ended up with up here when we selected our root. So we choose that value of m, and that becomes our new refractive index. Let me explain that one more time. We have 2 points. The second point's an unknown at this point, but we can do sort of a curve fit, and we're using a Taylor series to do that. The form of that Taylor series we reduce to a binomial function, so it's a second order polynomial. That has 2 possible solutions. We pick whichever of those solutions that gives us the imaginary component closest to what we already calculated it should be. So that selects our root. Next, we need to choose the branch index m. So on the first step, where we chose which of our roots, that also chose a real part. We choose an integer m that makes the real part closest to that. If we're doing a curve fit and our frequency points are close enough, it really shouldn't deviate that quickly that it jumps 2 or 3 values of m. It will only jump 1, and we pick the one that's closest. What we just discussed is all well and good, except that it required us somehow to magically know the refractive index at that first point, where we don't have additional information to figure out what's going on. So the next discussion we need to have is resolving the branching at that first frequency point. So let's just review some things. If somehow we knew the refractive index and impedance, the complex refractive index and complex impedance, we can calculate the complex permeability and permittivity from these equations. Well, if we plug in real and imaginary parts, what we can see is that the imaginary part of the permeability in terms of refractive index and impedance is this, and the imaginary component of the dielectric constant in terms of impedance and refractive index is this. Now, why are we looking at the imaginary components? Remember, we're assuming passive materials, and these two numbers have to be positive quantities. So if we have a passive material and these two quantities are positive, that implies that the product of the real part of refractive index and the imaginary component of impedance, the absolute value of that has to be less than the imaginary part of refractive index times the real part of the impedance. And we are going to use this condition to sort out what's happening at the first frequency point. Okay. We have our first frequency point. We are going to choose the branch index M that satisfies this equation we just arrived at on the past slide. Given that, we may not be done. There's two things that can happen at this point. Maybe there's only one value of M that does satisfy that. That's the ideal case. That's great. We have the correct answer, and we can go on. More likely, there's multiple correct solutions. And what we have to do is choose one of them, then go on to the second frequency point and generate our refractive index versus frequency. Go all the way back to the beginning, choose our other possible value of M, finish the rest of the process with all the other frequencies, and compare those lines with all the different possible values of M. The correct choice of M is the one that once we reconstruct the material values of all the other frequencies, it's the one line that satisfies this equation over all of the frequencies. So there's a lot of work here, and the reason there is this amount of work is because waves repeat every 2 pi, and there's just multiple correct answers, and we have to sort that out to get a correct answer. So here's an example in Physical Review, volume 70, and they did a parameter retrieval. And this is a really good paper to read, and I definitely suggest following it. I'm not going to spend too much time here. I'm going to go on to the other methods, but I definitely recommend looking up this paper and reading through it. Our next technique for homogenization or a parameter retrieval is something called field averaging. And a lot of the concepts, diagrams, pictures, equations, and particularly the examples at the end, I'll be taking from the reference at the bottom here by Smith and Pendry. So I'm not bothering on the following slides to keep referencing that, since I'm taking them all from the same reference. So this entire section, just consider each slide referencing that paper by Smith and Pendry. A real neat thing about field averaging is that it doesn't involve any branching. We don't have to sort that out. It falls out of the mathematics automatically. It's a very accurate method. Drawbacks is it's rather computationally intensive, and I would say this really only applies to simulations. We can't go into the lab measuring scattering parameters and use this to retrieve our field values. Now, in principle, maybe this would be possible. Maybe we could probe the perimeter of our cell and measure the complex field profile on the outside of a unit cell and retrieve our effective properties. But I'll say this essentially requires simulation and can only be done in simulation. So here's the process. Through simulation, we will build in a unit cell in memory, and we will use periodic boundaries around the outside, so it's an infinitely periodic structure. And we calculate that zero order mode. We calculate the block mode, and we know we want to calculate the field everywhere throughout that unit cell. So that's the first step. We give it a block wave vector, and we calculate the block mode. The second thing we'll do is we will average the fields on the outside of this unit cell. We'll talk more about what happens there. But once we have these average properties, it turns out we can readily calculate the average material properties of that mode. And those are almost the effective material properties. What we'll see, the equation we end up with the end, that is giving us these average material properties are the same exact equations that we used for finite difference frequency domain. We know from finite difference frequency domain, due to numerical dispersion, that a wave artificially slows down on a Yee grid. So if we are using this to extract material properties, we know those material properties will be slightly larger than the actual effective material properties, just due to the way we're extracting these using a Yee grid. So the last step, using concepts we discussed last semester in computational electromagnetics, we remove the numerical dispersion from that, and we end up with the effective material properties. So that's the flow for field averaging. Before we step into this, let's review Stoke's theorem. Stoke's theorem is something from vector calculus that lets us convert a surface integral to a closed contour line integral. And we will apply this to Maxwell's equations and end up doing line integrals around the perimeter of our unit cell. So that's Stoke's theorem. Converts between a closed contour line integral and a surface integral. So let's start with one of Maxwell's equations. We'll start with one of the curl equations, calculating the Bx component from the curl of the electric field. Well, we can integrate this over the x equals 0 surface. So I'm outlining the surface, and we will integrate both sides of this equation over that surface, and we end up here. Now we will apply Stoke's theorem. We'll look at what's on the left-hand side. Using Stoke's theorem, we can convert this surface integral to a closed contour line integral. So now we will be integrating around the perimeter of that face. We won't be integrating throughout the surface anymore, just around the perimeter. So this surface integral separates into 4 separate line integrals. And then the right-hand side, we still have our surface integral. So here's our starting point. Just to visualize where all the different terms are coming from, on the left-hand side of that equation, we had our 4 line integral equations. So this equation is integrating along this top line. This equation is integrating along this line. Notice there's a positive sign here because we're integrating, in this case, in the counterclockwise direction, which is in the positive y direction. So we have a positive sign here. Now we'll be integrating in the negative z direction, so we have the negative here. So we see the positive and negatives depending whether we're integrating in a positive or negative direction. So we have our 4 terms going around the perimeter of that x equals 0 face. And finally, this last term is calculating the B field at this center point, or integrating the B field throughout this entire surface to essentially arrive at the average value in the middle. So here's where we are. This is the equation we had 2 slides ago. We just drew pictures of what all these different terms can mean. So we look at this first term, and we see we're integrating e sub z from 0 to a along the z-axis. So we will interpret this integral essentially as the average z component of the z field at this point, 0, 0, a2. So that's at the center point of that line around the edge. Likewise, our second integral is the average at 0a, comma a2, and so on. So what you can do is click back to the previous slide and see how these 4 different properties actually fall in the middle of all these different faces. And then this last term we're interpreting as b sub x at 0, a over 2, a over 2. Again, click back to the previous slide and look at these relative to the pictures, and that will become apparent. Okay, so this top line, this is where we were a few slides ago. We now are interpreting these as averaged field values, so we plug in our average values. And now we divide both sides of this by a squared. And we end up with this final equation. If we stare at that long enough, what we'll recognize is that is an exact finite difference equation that we covered in finite difference frequency domain last semester. And our fields are staggered on a Yee grid. The positions that we calculated them are consistent with that. And since it's on a Yee grid, it's also suffering from the numerical dispersion due to the Yee grid. So in this case, we interpret A as our grid resolution that we did last semester, delta X, delta Y, and delta Z. So we did this for one face. We do it for all 6 faces, and we come away with 12 different field quantities. We have 6 components, or the 3 components of the E, the 3 components of the H, 3 components of D, and 3 components of B. So the E's and the H's are calculated from the line integrals. The D's and the B's are calculated from the surface integrals. So at this point, once we know the field throughout the unit cell, in fact, we really only need to know it on the perimeter of the unit cell, then we do our averaging to calculate those field quantities that'll be in the exact same positions that they would be in a Yee grid cell. Now we look at our constitutive relations. To make this work, we really need to generalize this to general bi-media. That means bi-isotropic and bi-anisotropic. And so here are those modified constitutive relations for bi-isotropic, bi-anisotropic materials. We know all of the field quantities. We know D, we know E, we know H, we know B, we know E, we know H. So in fact, we can solve these to calculate our 3, epsilon, mu, and kappa, our 3 different tensors. So at this point, we know our average material properties. We're not quite there. We know from last semester there's numerical dispersion on a Yee grid. In other words, even if we set our grid to all free space, just due to the interaction of the numerics, our wave is traveling slightly slower through our Yee grid than it would in real life. So that means the average material properties, which we think might be our effective material properties, are slightly too large. And we go back and we borrow what we discussed last semester for compensating for grid dispersion to adjust those material properties so we get the actual effective material properties of that unit cell. Just to review what happened there, we look at the dispersion relation that's the actual physical dispersion relation for a real material. The equivalent dispersion relation on a Yee grid is this. We really want these to be the same, but they're not due to the interaction with the Yee grid. So in fact, if the wave slows down, it's no longer traveling at the speed of light, it's traveling at some slightly slower velocity. And that's because the mu and epsilon are slightly larger than they should be. And we're going to use this to calculate a factor by which we can correct for that. So we'll solve the dispersion relation for the velocity v. Well, we know that should be the speed of light, but it's not, because our mu's and epsilons are a little bit bigger than they should be, so our velocity is a little bit slower than it should be, and we can calculate a factor gamma by which that slows down. So this might be something like 0.99 or 0.98, just slightly slower than the speed of light. Well, now we can solve this equation for gamma, and we have a nice expression to calculate what that constant is. In an ideal world, or as we take our grid resolution and go out to infinity, that gamma approaches 1. But the reality is it'll be slightly smaller than 1. So how do we use this? Well, we just calculated what we call our averaged material properties. From those, we calculate the final effective properties of our unit cell. And how do we do that? We take the average property we're interested in, we multiply it by gamma. Remember, these are slightly larger than they should be. This gamma will be slightly less than 1, and we get our effective material property. So we would just multiply all of these by gamma, and we have our effective material properties. And that is parameter retrieval through field averaging. Now, the Smith and Pendry paper that I referenced above, they have a few examples. Here's an example of a Maxwell-Garnett medium, and they have a sphere in the middle of a unit cell. And if we use the Maxwell-Garnett theory, here's what we would calculate as our effective permittivity or permeability. Well, as they increase the parameters of the unit cell, we can see that those deviate, and that's because we're deviating from what would be a truly Maxwell-Garnett medium. But we do see, as the d over lambda wavelength approaches 0, that it does actually approach Maxwell-Garnett. So let's think about what this is. When d is 0, that means our unit cell is very, 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 very short relative to the wavelength. And that's a requirement of the Maxwell-Garnett. This is really, really sub-wavelength. So the parameter retrieval is working. It's only when the periodicity starts approaching and looking photonic crystal-like that it starts to deviate. Remember this wire medium for having an artificial plasma frequency. Well, we can calculate sort of analytically our artificial plasma frequency, and that is this dashed line. We can do parameter retrieval now two different ways. We can use the S parameter retrieval method or our new field averaging method. And what we see is that the S parameter field averaging virtual overlay here, and same thing for the permittivity. So it is working, and we don't have to sort out the branching. And the final example here is on a split ring resonator, and what we're looking at on the right, these are the retrieved properties of mu and epsilon. Our next method is parameter retrieval through the T matrix, or transmission matrix. And maybe this is a little bit of an extension or generalization to the S parameter retrieval method, but it's worth discussing in its own section, I guess. So let's think about what the transfer matrix algorithm is. We have a unit cell, and maybe it's very complex, and we'll divide it up into layers. We'll step through that just like we did last semester. And eventually we have a transfer matrix that relates the fields at the first surface of that unit cell to the fields at the last surface. So the fields on the right are related to the fields on the left through this transfer matrix. Well, it turns out this is an eigenvalue problem. And this little complex exponential term, those are our eigenvalues. So if we solve this as an eigenvalue problem, we get these complex exponentials as our eigenvalues. So given the eigenvalues, we can then invert to calculate the effective refractive index. However, there's still branching here that we'd have to sort out. And we sort it out using similar ways that we discussed in the S parameter retrieval method. Well, in practice, we know the T matrix algorithm isn't stable. It's great and simple in concept, but what we can do is modify our scattering matrix algorithm to make it look like the T matrix algorithm, and this is numerically stable and robust. So using techniques that we discussed last semester in computational electromagnetics, we know we can describe a unit cell as a bunch of individual layers, and we can step through those, calculate the scattering matrix for each individual layer, and slowly assemble this overall scattering matrix for a unit cell. And so if we do that, we end up with exactly that, our scattering matrix for a unit cell. The next thing we'll do is we'll write this block matrix equation as two separate matrix equations. We will shift terms around and then put it back into a block matrix form. Notice what we've done here. Now we have in one column vector the mode coefficients at the entrance surface to our unit cell, relating the mode coefficients to the exit surface. So we're almost in the form of a transfer matrix. And in fact, if we brought one of these matrices over to the other side, we would have a transfer matrix, but we don't need to do that. If this is the scattering matrix for a unit cell, and if it is infinitely periodic, then these two mode coefficients are related through the block theorem. There's a periodic boundary condition here. So what is that periodic boundary condition? Well, we have the mode coefficients at the initial surface. We would add phase to that, and Kz is the thing we want to find. That's what we'll extract our effective material properties from. So these accumulate phase through the unit cell and gives us the mode coefficients at the exit phase. So we can think of Kz as the effective propagation constant, and from that we can extract the effective material properties. Given that boundary condition, we can now write that scattering matrix equation that we rearrange to more like a transfer matrix equation. We can write that solely in terms of the mode coefficients at the entrance phase. Well, when we do that, we have what is called a generalized eigenvalue problem. And again, we can solve this. This complex exponential is our eigenvalues. And just like on the first slide in this section, we can invert that to calculate our effective material properties. But there's still a branching problem because we have to invert that complex exponential. And the last thing I'll mention, and this is something pretty easy that comes up a lot that we can do, and that is Z uniform media. So in other words, our entire unit cell, if you will, is just one layer. It's uniform in that Z direction, that main direction of propagation. Subwavelength gratings, that's Z uniform media. When you're in the grating layer, it's uniform in that Z direction all the way through. And we know from our discussion with method lines and rigorous coupled wave analysis, what we're effectively doing is solving an eigenvalue problem in the cross-section and calculating all of the modes that can exist in the cross-section. And it turns out the eigenvalues that come out of that are describing propagation. And, like before, we can extract our effective material properties from those eigenvalues. Now, this is really simple. The drawback to this is this only works for relatively deep gratings. If we're shallower than, let's say, a quarter wavelength, remember from our discussion of sub-wavelength gratings, that's when there's some additional physics happening here. The percentage of power inside the grating becomes less significant, and we saw that the effective material properties deviated pretty sharply. So this is really good for estimating the effective material properties for deep gratings and long uniform media. Not so good for real shallow. This is a pretty quick section. The next approach we'll talk about for parameter retrieval is through optimization. And in optimization, we sort of circumvent the whole branching thing and having to sort out these complex exponentials, and we treat it like an optimization like we talked about last semester or even some this semester. And we're making random guesses somehow at the effective properties, and we fit those to our measured values, and we do a best fit. And in the end, what we end up with are our effective material properties. So here's a quick block diagram of how this could happen. So we'll start off and make an initial guess at the effective material properties, mu and epsilon. Then what we'll do is we will model a homogeneous slab made of those materials. We'll calculate the scattering parameters. At that point, we will compare those scattering parameters to some target scattering parameters. So these are either measured in the lab or simulated from the actual metamaterial, and we compare that to what we just got for this homogeneous slab. And if they match, hey, we're done. If not, and they probably certainly won't in the beginning, we somehow refine those. And the manner in which they're refined really depends on our optimization algorithm. We could use particle swarm optimization, genetic algorithms, gradient descent, a variety of other things. But in some way, we are intelligently refining that guess at mu and epsilon. Then we come back, we resimulate that homogeneous slab, we do some kind of comparison. If we're done, great. If not, we refine again. And we keep doing this until eventually our mu and epsilon produce a slab that gives us the same scattering parameters that we either measured or modeled from our engineered material, and the algorithm is done. So while this may take many iterations, we're not playing with complex exponentials and really trying to manually sort out the branching. Where this is done a lot is in ellipsometry, and essentially we shine a frequency on some engineered material and we look at what gets reflected and or transmitted, and we sweep either frequency or angle or polarization or all of the above. Then we use something like a Lorentz-Drude model So rather than directly iterating mu and epsilons, we're iterating the Lorentz-Drude parameters, and we're using that as an optimization. And we play with those until the Lorentz-Drude predicts a frequency sweep that matches either our measured or simulated from the engineered material. And the optimization works on the Lorentz-Drude parameters, not directly the mu and epsilon. So, in fact, ellipsometers are most commonly done at optical frequencies, but here's one that works at radio frequencies. But it is an ellipsometer. And what we see is we have a transmitting and receiving horn. I don't know which is which, but these will change angle. So we can actually sweep angle of incidence. They're probably also sweeping frequency. The sample that we're interrogating is down here. And that's a microwave ellipsometer. And right now, that's probably one of the best ways to measure material properties. In the research we do for 3D printing, this approach doesn't work so well because it requires very large samples. If we're 3D printing, usually we can only produce very small samples, and unfortunately we're forced to use other measurement techniques. Our next parameter retrieval method is something we use on our anisotropic metamaterials. And these are so sub-wavelength, it turns out there is no branching. So this is a little bit easier case, and we can retrieve the parameters quite a bit easier. Let's think about doing parameter retrieval using plane wave expansion method that we talked about last semester. Just to review what happens here, and we will wrap a black box around the actual solution to the wave equation. That happens inside the plane wave expansion method, but suppose we have this magical eigenvalue problem solver. We hand it two pieces of information, a description of the unit cell and a block wave vector. Remember, the block wave vector is conveying two pieces of information, the direction of this wave and also the period of the wave. So we're asking a question. We say, here's this unit cell. I'm interested in a wave going in this particular direction with this particular spatial period. What on earth could do that? And so the numerical crank turns, and out comes the answer to that, which is, oh, all of these different frequencies have modes like that. And by the way, the eigenvectors, here's what those modes look like. So the eigenvalues are the frequencies of those modes, and the eigenvectors are what those modes look like. And there should be an infinite number of modes. Now, on a computer, numerically, somehow we've discretized our problem. We really can only calculate a finite set of those modes. But in principle, there's an infinite number of those modes. We give it the block wave vector. The block wave vector is 2 pi over the period of that wave. If we know the frequency of that wave, we will know the free space wave number. The frequency of the wave will come out in terms of the eigenvalue. So at first we'll give it a block wave vector. The plane wave expansion method, or whatever we use to solve the eigenvalue problem, calculates our free space wave number. And so the block wave vector is the free space wave number times the effective refractive index of that mode. So we solve this for the effective refractive index, and it's the magnitude of our block wave vector divided by our eigenvalue, if you will. In fact, our eigenvalues are usually k0 squared. We'll take the square root of that to get the actual free space wave number and divide by that. Now, in order to circumvent branching, we make our block wave vector very, very small, 0.0001 or something like that, in terms of the 2 pi over the lattice constant times 0.0001. When it's that small, we're talking about a block wave whose wavelength is so large relative to the unit cell, it's really just seeing the effective or the average material properties. Now, if the unit cell is sized more comparable to the wavelength, like in a photonic crystal or some metamaterials, this is not a great way to do this. But for our anisotropic metamaterials that are extremely sub-wavelength, this is a great way of doing that, and there is no branching. So I have an example in a following slide, but roughly, if we have something that's anisotropic, we have up to 3 tensor elements that we have to somehow extract. But we can't tell it the polarization of the mode. That information comes out in the eigenvector. So we'd give it a block wave vector, we'd come out, we would in principle have to look at the polarization, and depending what direction the block wave is polarized, we would assign that effective material property in that particular direction. But it turns out, for a lot of cases, we don't even have to do that. We can do some intelligent design of our process that circumvents having to look at the eigenvector. So let's look at how that happens. Suppose we have a uniaxial metamaterial. How can we use the plane wave expansion method? How do we use this low frequency approximation to extract the tensor elements from that uniaxial metamaterial? So we start off with our uniaxial metamaterial. We see that we have this infinitely extruded direction in the z direction. So we can really reduce this down to a two-dimensional unit cell, where that third extruded direction is coming out of the plane right now. So this is our unit cell. The next thing we want to do is define a block wave vector. So the maximum value for a block wave vector is approximately 2 pi over a in the x direction. If you have a symmetric Brillouin zone, that might be pi over a. But we want to make the magnitude at the absolute largest, like 0.01 of that, 0.000, 0.40, 0.0001, something like that. Make this very, very small. When that is very, very small, that means the wavelength of the block wave we're trying to calculate is very, very large relative to the lattice spacing. And that's what we want. That's where the wave really is just going to see this averaging effect. There will be no resonance. So this low frequency limit is when there are no resonance conditions, and it's just seeing this material averaging type effects. So we choose a block wave vector, and in this case, it does not matter what direction the block wave vector is in. So we can choose any direction. I wrote x here, but it can be anything. The other thing is, we only need a single value. We're not calculating a band diagram or any kind of frequency sweep or anything like that. We just need one value. We'll call the plane wave expansion method, as you'll see, twice, once for the E mode and once for the H mode, and then we have our tensor elements. Okay, on to step 3. So we have our block wave vector, that's shown as this green vector, and we solve it for the E mode. Now remember, the E mode, that has the electric field out of plane in this Z or extruded direction. So we're talking about an electric field that's oscillating in this extruded direction. That means the effective index we calculate from that will be the extraordinary refractive index. And so we calculate the refractive index as the magnitude of this block wave vector we define, which is very small, divided by the frequency that we've just calculated. And that gives us our effective refractive index for the extraordinary mode. We do the exact same thing again, but now we're solving it for the H mode. Remember, the H mode has the H field out of plane. That means the electric field now will be in plane. And so, again, it does not matter what direction the block wave vector is in, as long as the E field is oscillating within this plane. In our metamaterial, we're talking about an electric field oscillating either up and down or in the horizontal plane. Any direction horizontally will all see the same effective refractive index in the long wavelength limit. So for this case, that gives us our ordinary refractive index. Well, our tensor element is just the refractive, our tensor down the diagonal is 2 occurrences of that ordinary refractive index, and then the last one is the extraordinary refractive index. And we're done. Next is a parameter retrieval method that's not discussed a lot, but I think is quite simple. It works real well and also avoids the branching. First, a preliminary definition. I'll talk about a parameter phi that I will call the single pass phase. And what we're talking about is a wave already inside our slab, and it traverses this just once, does not exit, doesn't reflect, just hits that second interface, but it accumulates a certain amount of phase just in this one pass. We'll call that parameter phi, as opposed to what I might call the device phase. We know a wave comes in here, it bounces around, it transmits, it reflects. We add up all the transmitted, we get an overall transmitted wave. We add up all these little reflected waves, we get an overall reflected wave. This reflected wave has a phase, the transmitted wave has a phase, but that phase has all of the bouncing and resonances and interference built into it. So I will call these the device phase, and this other phi the single pass phase. It's important to distinguish those two, or there can be some confusion. So let's think about what happens in a material when a wave propagates some distance d. Well, if this is a homogeneous slab, there's not a whole lot interesting. The only thing that happens is that the wave accumulates phase. And so here we're looking at a single pass phase. So what is that phase? Well, if this material has a refractive index n, then the amount of phase that accumulates is the free space wave number times the refractive index times the distance that the wave traveled. Now, the amount of phase, we like to bound it between negative pi and pi. So it's certainly possible, if this distance is long enough, that we might accumulate 6 pi of phase. Well, if it repeats every 2 pi, that really means we've accumulated 0 phase. Now, because this is a wave, this leads to the branching. There's multiple amount. If we're given 0 phase, that doesn't necessarily mean 0 phase. It's 0 phase plus an integer multiple of 2 pi, because we're talking about waves. So there's multiple correct solutions again, so this branching thing leaks back in. And we want to get rid of it. We don't want the branching. We don't want to have to deal with it. Before, we resolved the branching by knowing additional information, and that involved information from different frequency points. A similar thing is happening here. If we look at our expression for that single pass phase, and if somehow we could extract that, and in fact we can quite easily without ambiguity, where the ambiguity comes in is this integer m. Well, what if we differentiated this equation with respect to wavelength? We would end up here. And this integer m term drops out. It's not a function of wavelength. It's gone. So really what we're saying is, let's look at the slope of the phase response and extract the effective refractive index from that. So if we take this equation and solve for the refractive index n, here's a way that we can calculate the effective refractive index of that homogeneous slab given the slope of the single pass phase. No branching problems. How do we get around the branching problems? Because there's additional information here. We have to calculate the slope of the phase. This implies we have to know it at more than 1 point, at 2 or 3 points. We can do a very similar thing, but instead of wavelength, we can do it in terms of frequency. And here's our final equation: effective refractive index in terms of the single pass frequency, the slope with respect to frequency instead of wavelength. Usually at radio frequencies, microwave frequencies, we like to think in terms of actual frequency. For optical applications, we think more in terms of wavelength. Both are equivalent. Both will give you the same answer. So let's do an example. Let's design a Bragg grating. And remember, a Bragg grating is alternating layers of dielectric slabs. Here we have low index, high index, low index, high index. And we're giving these refractive indices of 1.5 and 1.51. So very close, right around 1.5. And we designed this to work at 1.5 microns, or 1550 nanometers. So we designed a Bragg grating, and we let it be 500 periods long. Let's look at the response of that Bragg grating. Here's the reflectance and transmittance. We're looking at the overall reflectance, the overall transmittance, and we're also looking at the phase. Remember, this is what we're going to extract our effective refractive index from. So we're looking at the phase of the reflected wave and also the phase of the transmitted wave. Let's look at the phase of the transmitted wave and see what's going on. In fact, the discrete jumps you see aren't really happening. Think this way. We have phase that's increasing, increasing, increasing. When we get up to pi, remember, we've bounded our phase from negative pi to pi. So it doesn't make sense for it to keep increasing. In reality, it does. So we jump down by 2 pi, and we keep increasing, 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 jump down by 2 pi. So there's what's called wrapping that's happening here. And we can unwrap this, and maybe it makes a little more sense. Here's the unwrapped phase as that wave is traveling through our Bragg grating. Here we see a nice linear response. And then we see around the region of our Bragg grating, something a little bit weird happens with the phase, and then we get a nice linear response again. These two are equivalent. It's just that this has been unwrapped. But if we take this curve and subtract all integer multiples of 2 pi, we would end up with a curve that looks like this again. So really these two are the same. But to run our algorithm, we need to unwrap it. First step in this, let's calculate the slope. Well, if we did a frequency sweep, we probably have a whole bunch of points here. We can use a simple finite difference scheme to estimate the slope. And that's exactly what we do. We take the data on the previous slide and we take the derivative. And here's what that derivative looks like. Now we need to add in those extra constants to actually extract the effective refractive index. And here that is. So this is the effective refractive index of a Bragg grating. Now notice, we built this out of refractive indices 1.5 and 1.51. So it makes sense that the average refractive index out here is about 1.5. That makes sense. But notice it spikes all the way up almost to 2 and goes all the way down to somewhere around 0.5. Let's try to reconcile this with the Wiener bounds. The Wiener bound said it can't possibly go below 1.5 or above 1.51, but it is here. Why is that? Well, the Wiener bounds only applied to a non-resonant device. A Bragg grating is a one-dimensional photonic crystal. There's resonance. So there's physics happening that the Wiener bounds didn't account for. So we can actually have effective properties outside the Wiener bounds, except we need resonance to do that. And that's where the photonic crystals come in. Some interesting things to note about this. Here we have a decreasing refractive index with wavelength. That's actually negative dispersion. That can be very interesting. And positive dispersion. These are very dispersive. When we get to slow wave devices, we'll look at this and we'll look for regions with dispersion and we'll say, oh, that's also where the wave is slowing down. So there's a bunch of interesting things happening here that's also very useful. And we could do a quick study. We could look at just the ordinary Bragg grating that we just did. That's called the baseline, and that's the blue line down here to repeat what was on the last slide. We could chirp the Bragg grating. So if we chirp it, that's the red line. We could use higher index contrast. We've doubled the index contrast now. And that's the black line. Notice we go much up, much higher. We go down much deeper. We get much more extreme values. So if we were designing something like a slow wave device, we probably want to use higher contrast. Well, what if we didn't change at all, just added more periods? That's the green line. And what we see is a little bit more extreme values as well. So let's conclude this lecture. I know this was a long one and the math is brutal. I did my best to simplify and draw things with pictures as much as I could, but there are some general conclusions to come away with here. The overall concept. We started with some kind of engineered material, whether this is a mixture, a metamaterial, a photonic crystal, but it had some thickness D and it has some scattering properties to it. If we can replace this with a homogeneous slab of the same thickness and get the same scattering response, whatever properties we use in here are our effective material properties. And that could be either mu and epsilon or refractive index and impedance. That's the concept behind homogenization or parameter retrieval. We don't want to have to model our metamaterial or engineered material. That's quite complex. We would love to just replace it with its effective material properties and go from there. We can get away with much coarser grid resolution and much simpler simulations. The last thing to come away with is parameter retrieval is plagued with the branching problem because we're talking about waves. They repeat every 360 degrees or every 2 pi. So we're just plagued with these multiple correct answer problem. And it's just ding dang hard to solve. And there's all these different techniques that circumvent it under certain circumstances. For example, our very low frequency method we talked about for anisotropic metamaterials, well, that doesn't apply to something that's resonant. We can't do that. So we avoided the branching by being very sub-wavelength. So I can't say that there's any one method that is superior to all the others, and the jury's still out to what's best. So all I can really do is just share with you some of the most dominant methods out there and kind of give you an idea or a theme of what's happening numerically. So that's it for this lecture.